Hi, my name is Torben Øverbekk. I work for Nanopower Semiconductor, and I'm here to demonstrate the nPZero configurator, which is a new tool that we made to help you develop and evaluate the solutions based on the Nanopower Zero IC. And what we try to do with this tool is essentially simplify the process of configuring our device. Because we have a datasheet which gives you information about all the registers, all the technical information, but this is very detailed and can be a bit complicated to get into. This middle view here is showing an overview of the registers, and this is very similar to what you would find in the datasheet. If you hover over any of these fields, you can actually get the description of it. You can see what different kind of values you can assign to that specific field. But then in order to make this easier to understand, we have this graphical representation on the left. And any change you make here will be instantly reflected in the register view. So you can see what all of these settings actually does in the registers. Similarly, you can also actually change the registers directly. And this will also be reflected on the graphical side. So any change I make here should be immediately updated on the graphical part of it. And then finally, we also have the code generator. So whenever I make a change to any of these settings, that will be reflected in the generated code. And then you can easily export that code to whatever kind of host MCU you will be using. So if it's a Nordic or an ST or potentially other architectures in the future, you can easily take this code. It's just standard C code, which integrates very easily with most of these SDKs. And then once you have made a prototype, you made a code, you want to test it, you can then go into this sort of testing mode. Let me just hide a bit here. Yeah. So let's see if this is actually running. So right now I'm running the evaluation board right here. So this is the nPZero evaluation kit. The chip itself is the one here. That's the chip that we sell. We also have a host MCU connected. So this is a host MCU that we provide as part of the kit. This is an ST MCU, but it's using a standard Arduino form factor. So this could be replaced with any kind of MCU like the Nordic or ESP or TI or whatever you want to use. It has 4 connectors for sensors. So in this case, we're just using one temperature sensor over I2C, but you can connect up to 2 I2C sensors and 2 SPI sensors to the evaluation board. And then on the left, you can see this small sniffer module, which I made based on the Nordic dongle. This one is connected to the I2C, to the UART, and to some of the enable pins for the sensors and the host. And that's why it can toggle the pins, or everything that happens on the board can be reflected in the interface over here. And let's see if it's actually connected. So right now we're sort of in sniffing mode, where we are evaluating what's happening on the connected evaluation board. And a typical application with this device, you will wake up the sensors at a certain interval. You will read the value of the sensors, and based on that value, you will either wake up the host or you will not. In this particular case, it will wake up the host every time. And usually what happens when you wake up the host is that the host will configure the nPZero device. And this is what is happening here. All these blue blocks signify I2C transactions. When I double click a box, you can see what it means up in the terminal. All the green boxes are UART log output. So this is the host CPU writing something to the log. And then I can see that this red line on the bottom is the host wake up, and the yellow line is the sensor wake up. And then based on the timing of these different events, I can then calculate an approximate power consumption of the system. You can see now that the I2C is about 800 nano average, a bit more on the logging. In this case, the host is on for a long time, so that is drawing quite a lot of power. And this is giving me a sort of diagram here showing what the different components are contributing to the power budget. And based on a typical coin cell battery, this would give me a battery life of 3 months or thereabouts. So then you can try to optimize these different things and get better battery life, basically. So this basically allows you to understand the chip, configure the chip, test it, and then do iterations where you try to optimize to get better power consumption.